Liquid crystals are matter in a state that has properties between those of conventional liquid and those of solid crystal. For instance, a liquid crystal may flow like a liquid, but its molecules may be oriented in a crystal-like way. There are many different types of liquid crystal phases, which can be distinguished by their different optical properties. When viewed under a microscope using a polarized light source, different liquid crystal phases will appear to have distinct textures. The contrasting areas in the textures correspond to domains where the liquid crystal molecules are oriented in different directions. Within a domain, however, the molecules are well ordered. LC materials may not always be in a liquid crystal phase. Liquid crystals can be divided into thermotropic, lyotropic and metallotropic phases. Thermotropic and lyotropic liquid crystals consist of organic molecules. Thermotropic LCs exhibit a phase transition into the liquid crystal phase as temperature is changed. Lyotropic LCs exhibit phase transitions as a function of both temperature and concentration of the liquid crystal molecules in a solvent. Metallotropic LCs are composed of both organic and inorganic molecules. Their liquid crystal transition depends not only on temperature and concentration, but also on the inorganic-organic composition ratio. Examples of liquid crystals can be found both in the natural world and in technological applications. Most contemporary electronic displays use liquid crystals. Lyotropic liquid crystalline phases are abundant in living systems. For example, many proteins in cell membranes are liquid crystals. Other well-known examples of liquid crystals are solutions of soap and various related detergents, as well as the tobacco mosaic virus. History. In 1888, Austrian botanical physiologist Friedrich Reinitzer, working at the Karl-Ferdinand-Universität, examined the physico-chemical properties of various derivatives of cholesterol which now belong to the class of materials known as cholesteric liquid crystals. Previously, other researchers had observed distinct color effects when cooling cholesterol derivatives just above the freezing point, but had not associated it with a new phenomenon. Reinitzer perceived that color changes in a derivative cholesterol benzoate were not the most peculiar feature. He found that cholesterol benzoate does not melt in the same manner as other compounds, but has two melting points. At 145.5 degrees Celsius it melts into a cloudy liquid, and at 178.5 degrees Celsius it melts again and the cloudy liquid becomes clear. The phenomenon is reversible. Seeking help from a physicist, on March 14, 1888, he wrote to Otto Lehmann, at that time a private docent in Aachen. They exchanged letters and samples. Lehmann examined the intermediate cloudy fluid, and reported seeing crystallites. Reinitzer's Viennese colleague von Zeferowitsch also indicated that the intermediate fluid was crystalline. The exchange of letters with Lehmann ended on April 24, with many questions unanswered. Reinitzer presented his results, with credits to Lehmann and von Zeferowitsch, at a meeting of the Vienna Chemical Society on May 3, 1888. By that time, Reinitzer had discovered and described three important features of cholesteric liquid crystals: the existence of two melting points, the reflection of circularly polarized light, and the ability to rotate the polarization direction of light. After his accidental discovery, Reinitzer did not pursue studying liquid crystals further. The research was continued by Lehmann, who realized that he had encountered a new phenomenon and was in a position to investigate it. In his postdoctoral years he had acquired expertise in crystallography and microscopy. Lehmann started a systematic study, first of cholesterol benzoate, and then of related compounds which exhibited the double melting phenomenon. He was able to make observations in polarized light, and his microscope was equipped with a hot stage enabling high-temperature observations. The intermediate cloudy phase clearly sustained flow, but other features, particularly the signature under a microscope, convinced Lehmann that he was dealing with a solid. By the end of August 1889 he had published his results in the Zeitschrift für Physikalische Chemie. Lehmann's work was continued and significantly expanded by the German chemist Daniel Vollander, who from the beginning of 20th century until his retirement in 1935 had synthesized most of the liquid crystals known. However, liquid crystals were not popular among scientists and the material remained a pure scientific curiosity for about 80 years. After World War II, work on the synthesis of liquid crystals was restarted at university research laboratories in Europe. George William Gray, a prominent researcher of liquid crystals, began investigating these materials in England in the late 1940s. His group synthesized many new materials that exhibited the liquid crystalline state and developed a better understanding of how to design molecules that exhibit the state. His book Molecular Structure and the Properties of Liquid Crystals became a guidebook on the subject. One of the first U.S. chemists to study liquid crystals was Glenn H. Brown, starting in 1953 at the University of Cincinnati and later at Kent State University. In 1965, he organized the first international conference on liquid crystals, in Kent, Ohio, with about 100 of the world's top liquid crystal scientists in attendance. This conference marked the beginning of a worldwide effort to perform research in this field, which soon led to the development of practical applications for these unique materials. Liquid crystal materials became a topic of research into the development of flat-panel electronic displays beginning in 1962 at RCA laboratories, when physical chemist Richard Williams applied an electric field to a thin layer of a pneumatic liquid crystal at 125 degrees Celsius. He observed the formation of a regular pattern that he called domains. This led his colleague George H. Heimeyer to perform research on a liquid crystal-based flat-panel display to replace the cathode ray vacuum tube used in televisions. But the para-azoxyanisole that Williams and Heimeyer use exhibits the pneumatic liquid crystal state only above 116 degrees Celsius, which made it impractical to use in a commercial display product. A material that could be operated at room temperature was clearly needed. In 1966, Joel E. Goldmacher and Joseph A. Castellano, research chemists in Heimeyer Group at RCA, discovered that mixtures made exclusively of pneumatic compounds that differed only in the number of carbon atoms in the terminal side chains could yield room temperature pneumatic liquid crystals. A ternary mixture of Schiff-based compounds resulted in a material that had a pneumatic range of 22 to 105 degrees Celsius. Operation at room temperature enabled the first practical display device to be made. The team then proceeded to prepare numerous mixtures of pneumatic compounds, many of which had much lower melting points. This technique of mixing pneumatic compounds to obtain wide operating temperature range eventually became the industry standard and is used to this very day to tailor materials to meet specific applications. In 1969, Hans Kelker succeeded in synthesizing a substance that had a pneumatic phase at room temperature, MBBA, which is one of the most popular subjects of liquid crystal research. The next step to commercialization of liquid crystal displays was the synthesis of further chemically stable substances with low melting temperatures by George Gray. That work with Ken Harrison and the UK Mott in 1973 led to design of new materials, resulting in rapid adoption of small area LCDs within electronic products. These molecules are rod-shaped. Some are created in the lab and some could appear spontaneously in nature. Since then, two new types of LC molecules were discovered, both are man-make, disc-shaped and bowl-shaped. In 1991, when liquid crystal displays were already well established, Pierre-Gilles Lejeune, working at the Université Paris-Sud, received the Nobel Prize in Physics for discovering that methods developed for studying order phenomena in simple systems can be generalized to more complex forms of matter, in particular to liquid crystals and polymers. Design of liquid crystalline materials. A large number of chemical compounds are known to exhibit one or several liquid crystalline phases. Despite significant differences in chemical composition, these molecules have some common features in chemical and physical properties. There are three types of thermotropic liquid crystals: discotics, bolics, and rod-shaped molecules. Discotics are flat disc-like molecules consisting of a core of adjacent aromatic rings. The core in a bolic is not flat but like a rice bowl. This allows for two-dimensional columnar ordering, for both discotics and bolics. Rod-shaped molecules have an elongated, anisotropic geometry which allows for preferential alignment along one spatial direction. The molecular shape should be relatively thin, flat or bowl-like, especially within rigid molecular frameworks. The molecular length should be at least 1.3 nanometers, consistent with the presence of long alkyl group on many room temperature liquid crystals. The structure should not be branched or angular, except for the bolics. A low melting point is preferable in order to avoid metastable, monotropic liquid crystalline phases. Low-temperature mesomorphic behavior in general is technologically more useful, and alkyl terminal groups promote this. An extended, structurally rigid, highly anisotropic shape seems to be the main criterion for liquid crystalline behavior, and as a result many liquid crystalline materials are based on benzene rings.